this talk, actually, I will talk of a different subject, how one can talk about, I will talk about rare events, what they are, and why regular, let's say, molecular dynamics or some other subject technique is ineffective to study this phenomena. And so I will talk briefly about a method which is implemented in the code to actually calculate energy barriers, and then from these energy barriers one can estimate transition probabilities for these rare events. Okay, what a rare event is? Suppose that you have, okay, this is in one dimension. Suppose you have a chemical reaction or suppose you have an energy landscape, and this energy landscape has regions corresponding to have several minima, and these minima are connected by regions where the energy is higher and is much higher than the typical thermal energy that you have in your system. So if in order to go from some reactant local minimum to the product local minimum, you need to go above and go up of an energy, of an activated energy, EA, which is much larger than KT. Then what happens is that this things occurs on a time scale which is extremely long. So basically what happens is that the system oscillate and live around a given minimum, and then every now and then, and this is typical time between different sequence transition is of the order of some typical fluctuation around the minimum times an exponentially large factor that is exponentially large in the ratio of the activation energy over the thermal energy. So this is something that was already, let's say, discovered and proposed in the late 19th century, and by Arrhenius and stuff. And typically, if we plug some number, so we say that typical fluctuations around you put some typical vibrational frequency, so this is something like of the order of 10 terahertz, so typical vibrational frequency around the minimum, and you say that the activation energy is a large fraction of an electron volt, and you are at room temperature. This makes that you will have a transition every second, around every second. Every second is not a very long time, you would say, but if you want to compare it with a molecular dynamics run, typically molecular dynamics time step is of the order of femtosecond or some fraction or a few femtoseconds, and so then you will need 10 to the 15 time steps of regular molecular dynamics to have a chance, a reasonable chance to see one transition in your simulation. Basically, almost always, the system will be vibrating around a given minimum, and then every now and then, very rarely, will jump. And then when the jump occurs, actually it is fast. So when the very unlikely fluctuations that allows the jump to occur, then the jump is fast, but it is extremely rare. So what is macroscopically perceived as a slow process is actually a fast but very rare event. So molecular dynamics is not the right way to do that. So people have found other methods, approximate methods to deal with this system, and the transition, and the harmonic transition state theory has been proposed and developed. And so basically, this say that this can be demonstrated with certain hypotheses using equilibrium statistical mechanics, and basically it says that the rate of the transition is the one that we have seen in the first slide, the one proposed by Arrhenius. Okay, that was the time. At the time, this is the rate, so it's the inverse. So the rate is something like that, which is exponentially small in this ratio, and with a prefactor which has the dimension of a frequency, and in this harmonic transition state theory can be shown to be basically the ratio of all the vibrations, all the normal vibrations frequencies in the reactant around the minimum, the started minimum, divided by the product of all positive, all stable frequencies around the saddle point. So in many dimensions, so in one dimension, these minima are connected by maxima. In many dimensions, many things may occur, but the most probable path that brings you from the reactant to the product is a path that I will introduce in a moment, called minimum energy path, that start from a region where all the derivatives or the curvature is positive in every direction, and then it will pass through a saddle point in which the curvature is positive in all directions but one, which is the direction of the which is the reaction coordinate at the saddle point. And so you have a saddle point in which only one of the eigenvalues of the second order derivative is negative, and so it is a stationary point in which only one eigenvalue in one particular direction of the second order derivative matrix is negative. So you throw away that one and you make the product of all the stable frequencies. So there are 3n minus 1, and so this is what you have below in the denominator of this ratio. So here you have 3n frequencies, here you have 3n minus 1 frequencies, so this is a frequency. And it typically is of the order of 10 to the minus 12. No, 10 to the 12, sorry, or 10 to the 12, 10 to the 13. So in the order of the terahertz. Yes.
In this kind of chemical reactions,
yes,
when we mix the reactants, is first get ionized and then come to the reaction.
Depends on the system.
For example, most of the acid-base reactions. Now, they basically go to the excited state.
Well, this is not. We are not talking about that. So we are not talking about reaction in which you excite the electrons. So we are.
Yes. Now, question is, even if you are not exciting, the reaction is still going on. Is there any reasonable logic to believe that these reactions are really Arrhenius type, not non-Arrhenius? And is there any also reason to logically believe that harmonic theory would work fine, because an harmonicity would be involved, and also non-Arrhenius type you cannot rule out. So what is the reasonable logic one can put?
Okay. An harmonicity, yes, you're right, that one usually, okay. The anharmonicity may, I think, modify this prefactor, but I think that the exponential term, I think, is anyway there. So by making the harmonic approximation in the minimum and in the southern point, you are making an approximation. This is true, but the fact that this configuration is exponential. So the transition state theory say that you basically have, in order to go, so the two conditions that the two hypotheses is that the hypothesis is that you have that equilibrium statistical mechanics is correct. So that the probability to find your system here or here is associated to the Boltzmann factor. So the probability to have a transition is related to the probability to be here and to be here with the right direction, with the right speed in the right direction, okay, and the right velocity. So the probability of being here is this, and this is the Boltzmann factor, and so this is something that one would expect to be correct anyway. The estimate of how, once you are here, how often you go in the other side, then gives you the factor. And so obviously, if your system is harmonic here and at the southern point, this is a good approximation. If it is not harmonic, it will not be a good approximation, but it will not be completely wrong. And if you are, and the main point is that when one calculates this transition rate, one typically is concentrate on the activation energy, which gives you the dominant effect. Because if you are wrong, if you are wrong in the prefactor by a factor of 2, this actually has a very little impact on the overall, but has an impact on the overall reaction. But errors in these terms are much more, are exponentially more important. So people, actually, whenever, very often when you calculate these things, you even not really try to calculate the prefactor, you just put some number which is of the order of 10 to the 12, 10 to the 12 errors. So, of the order of the terahertz.
So as you said that this Boltzmann factor in the exponent is really the predominant.
Yes, yes.
But that
for the excited state thing, you're right, but I think this is a different subject in the sense that here we are moving in the Born-Oppenheimer potential energy surface, so we are always moving in the ground state Born-Oppenheimer potential energy surface. What you are referring to is important and is the non-adiabatic excitation. This is something that one should in principle take into account, but I don't know. People usually do not do that, or only in very simplified situations I think it's possible to do that.
Even in the Boltzmannian distribution, it gives you a kind of ensemble.
Yeah.
As you were saying that e to the power minus EA by kVt is protected.
Mm-hmm.
But if I put, for example, in the exponent EA by kVt, a small alpha, stretched exponential, even then it would be protected. but the system would decay in non-debio. How to incorporate that? Suppose it may have some reactions in which Boltzmannian thing is protected, but with a very slow decay rate. How do you configure that?
This is some, no, I don't know how to.
So in quantum espresso it has not been.
Well, in quantum espresso what we do is to calculate the activation energy, then you can put to whatever exponent you want. But I mean, you need to have a physical reason to do that, and I don't know how to comment on that. So, okay. So the main thing to calculate are this factor and this activation energy. Actually, as we were discussing, the activation energy is the most important thing because the factor can be calculated. In principle, you need to calculate frequencies. This can be done with quantum espresso. We will see tomorrow. But let's say the dominant contribution comes from the exponential term, and this is what one wants to do. In order to calculate these activation energies, you need to locate the saddle points. And the problem is that saddle points are not easy to calculate, to locate, because contrary to local minima, that for which methods like the FGS and steepest descent or time dynamics may work, you need to find a stationary system, but which in some direction is a minimum and in some other direction is a maximum, and so it is not easy to do. So suppose you have a multi-dimensional system. This is simply a two-dimensional system, but already you have a number of local minima in red, a couple of saddle points, and what you are interested in is the path that gives you the highest probability to go from reactant to product, and one can show that this path of highest probability is the called minimum entry path. That is a path that goes from reactant to product, where the component of the force that are orthogonal to the path are all zero. So the path is some path. For which the force, so the gradient, the local gradient of the potential energy surface is is parallel to the path itself. So there is no component, orthogonal component to the path. So tau is the local tangent, and gradient of V is the local gradient of the potential, and the condition to be a minimum energy path is that this is zero. What can be shown is that if you are able to find this minimum energy path, then you have solved your problem in the sense that this one goes through the saddle point. How do you do it in practice? Okay, in principle, this is a problem in functional analysis. Everything is continuous. You have to set up a functional and then minimize in the space of functions of paths. What you do in practice is that you discretize. So you define a position, a path variable that goes from, let's say, from 0 to 1, from 0 in the reactant to 1 in the product, and then that parametrically define a path which is defined by several positions in your configuration space. You can define the local tangent by simple, even not very accurate definition of the derivative of the path with respect to the position. And then you can calculate the forces in the different points and calculate the orthogonal force, and then you condition that you have to do to impose is this minimum energy condition. One possibility is to do simply steeper descent. So you simply do, you have a certain estimate of a given point, the next estimate will be some coefficient, fixed coefficient in the direction of the path. The problem is that even if you have tried as much as you could to eliminate the tangent component of the force, there always will be, for numerical reason or because this tangent is not very well calculated, because the step size is finite, etc. There will be always some residual component that will actually tends to bring you down. So you have started with a chain, let's say. Suppose you have started with some discretization of a path that goes from here to here, and then you have divided it in 10 configurations. Then you calculate the tangent, you calculate the forces, and you move them according to the orthogonal forces. But sooner or later, what will happen is that a number of images, a number of these replicas of the system will collapse in the products, another number will collapse in the reactant, and then you will not really have a path. You have simply a bunch of points that goes into some local meaning. So how do you prevent these images, these replicas of your system to collapse to the minima? You have to tie them and force them to stay in line. I mean, to not fall apart. So what you do is that you connect the subsequent. I think I go here maybe. Yeah. So let us connect subsequent images by some string. So we simply tie subsequent images, and we add some penalty when you pull them apart. In this way, you will prevent the system to break and have a subset of the images going in one direction and another set of the images going into the other direction. The important thing is that these springs should not interfere with the minimum energy path condition. So the minimum energy path condition is on the orthogonal component of the force, and instead what you want is that your spring will actually act in the direction of the tangent. So you want basically you want a penalty whenever you elongate the spring, but not a penalty when you move the spring, when you rotate the spring. That would give you force in the tangent in the orthogonal direction. So basically what you do is that you add springs, and this spring only act, and then you project the force that you would obtain from the spring along the path. And then now the minimum energy path condition is in the orthogonal condition is simply the usual one. So the total force will be 0 when the orthogonal force is 0, and when the tangent force will be such that the image is pulled in the same by the same amount by the two images, that the one that preceded and the one that followed in the spring in the chain. and this term will enforce that the images are more or less equispaced in the along the reaction coordinate. Okay, so this is basically the nudge elastic method, band method in one slide, and then you need to define how you move it. And for instance, you can have steepest descent or quick mean or some kind of Broyden. Okay, these are different methods that are implemented in the code, so you can just choose one or the other. But the main thing, important thing, is that you have to not only to look at the tangent, the orthogonal forces. So you have to minimize the orthogonal forces, but to zero the orthogonal forces, and also you have these springs that keep the images.
Capital K is spring constant.
Capital K is a spring constant, and in principle you can have different springs, and this is indifferent for different pairs that link different pairs of
So spring constant is anisotropic.
Spring constant is it's again an auxiliary thing. So in principle you could be very smart and define it in a very clever way. What we have is that it is isotropic in our case, and but it is, anyway, it is projected on the tangent. So this is something that is basically one-dimensional, only along the path. So this is something that the only reason it is there is because we do not want the two subsequent images to be pulled away one from the other. So if you pull the two images away, this will cross quadratically, and then you pay a price. And this price, eventually it will become too large, especially if K is large. And so the larger is K, the closer you expect to find the two images. Okay?
So K is, in a sense, is a restoration.
Yes, and is what keep the images close together.
So that the Hookean spring system is valid.
Yes, it is explicitly quadratic. So it is an artificial thing that only acts along the reaction coordinate, and does not interfere, because this is projected along the path and this is projected orthogonal to the path, does not interfere with the other condition. So when you do that, you start, let's say, with something like that, and then at the end you obtain a path like this. So this is, let's say, the coordinate along the path, and this is the energy in some unit which is not really relevant because this is anyway some other potential. But let's say you start from some approximation for the path, which has a large barrier, because here you pass through some place here which is very high in energy, and then by defining this nudge elastic band and then minimizing its energy in the way I was describing, then you optimize the path, and in the end you get something like that goes through the different extreme, both the local minima and the saddle points. In particular, through the highest saddle points, that in this case is this one. So the activation energy is basically something like that.
So when it reaches towards the local minima, how you kick it out?
No, you don't. When do you want to keep them out?
Because if it's stuck in the local minima, stay there for some time until it gets the jump to go.
This is what will happen in reality. I mean, you have your system that will have to overcome this barrier to go here, and then to overcome this other barrier to go there. This is what will happen in reality. So, but if you calculate the transition from here to there, this I think should be the right, because if you have at a temperature large enough that this has any chance to occur, then these two will be basically equilibrated. So you can estimate. So the probability of making this jump will be related to this activation energy, and the probability to be here will be related to the Boltzmann factor between these two, because they are equilibrated. And so in the end, the probability to make this jump is going to be related to the sum of the two. So I think it should be, usually one actually try to locate one saddle point at a time, because this is the elementary step. Okay, this is a toy model and has 2 dimensions and so on. Yes?
For each point in that formula that you gave, you basically connect a spring to one neighbor.
Yes.
You wanted to pull it.
Well, this actually is not really correct. Well, I mean, you should have a sum of all the springs. So here you have actually each image is pulled by the previous and the sequence. Yes, you're right. This is not totally correct the way I wrote it. This is sum over all the springs, but the spring only connect subsequent images. You're right.
So how did you locate the saddle point?
Well, at the beginning, okay. This will converge to some minimum energy path.
Yeah, but you know the minimum energy path.
And it will converge starting from some initial guess that is by default it is just a linear interpolation between the two initial and final states.
You mean the code will automatically search the real minimum energy path, or you have?
Well, this is even a more difficult problem than looking for the global minimum that Romana was mentioning before. In the sense that we are not looking for the global minimum, but in principle we are looking for the smallest. I mean, for the saddle point that has the smallest activation energy.
Yeah.
Here, in principle, there is only one path that goes from here to there. Let's say that only one minimum energy path, but you can imagine that there may be other local minima, that may be some alternative choice that is completely different, topologically completely different, or even not even you don't need that it's topologically different, but it may just be different and go through some other saddle point, and depending from which guess for the path you start from, you can fall in one or the other. So this is an even more, in general, more complicated problem than locating the global minima. In global minimum in a multi-dimensional system, what you do is to try to be guided by some chemical intuition or something like that. Or either you just do this. What you can do is to define some intermediate image in our code. What you can define is some intermediate step. So you can say that I know that the first bond that breaks is this one.
Yeah.
And so I add one image, let's say, in the right direction, in the direction that I think is the right, and then the program will assume a starting path that linearly interpolates between what you propose. And then by changing these things, you can explore the system, and then you will have to find either everything anyway go in the same final landscape, or you may have different alternative solution, and then you have to choose the one that gives you the smallest activation energy.
So basically what you are saying is that you really need a very good initial guess, right?
Sorry? You need to be able to vary the initial guess, but this is possible. I will tell you how to do. There is another way that one could think is a good one. Suppose we have this system, and we say, okay, I want to go from here to here, so I don't really want to think too much about this minimum energy path. I just go step by step in this direction, and then I minimize in the orthogonal manifold. And then if I move here and then I minimize in this orthogonal place, I go there. If I do this here, I go here, etc., etc. And then when I arrive here, I will be basically, obviously, in this direction, the minimum will be at the transition. Well, obviously, it's not obvious, as you will see, but in this particular case, this is what happens. So doing constraint minimization, so you choose a reaction coordinate or some tentative reaction coordinate, and then you minimize in the orthogonal direction, and then you draw the energy as a function of this of a variable that goes from 0 to 1 in this variation of the approximate reaction coordinate, and actually it is not that bad, because in this particular case the two method gives basically the same value for the saddle point, and they locate the same saddle point. So why do we need all this thing that is complicated, convert very slowly and things? So why cannot just reduce ourselves to make many constraint minimization? Because there are cases where this doesn't work. Suppose we have a landscape like that, so with a minimum here, another minimum there, and then some saddle point in between. But somehow with this shape, if you one could say, okay, my reaction coordinate, I approximate my reaction coordinate by this linear interpolation, and then I minimize in the orthogonal direction. And so if you see, what happens is that when you are on this side of the, up to here, you actually are collapsing, you are minimizing, and you are collapsing in this long valley. When you are above a certain point, you are collapsing in this other valley, and you never have something that approach the real saddle point, and you have a sudden jump at a given point. So the coordinate, so this is not a path, this is something that continuously vary up to here, and then at a certain point jump on the other side of the mountain, and then go back to the minimum. And then if you draw the two things, the nerve instead works properly, and so estimate correctly the activation energy, so locate it correctly and estimate correctly the energy, while the constraint minimization, even a very dense one with 50 images, is completely wrong. And also, basically, it's completely wrong, does not go to the minimum, and you have sudden discontinuous jump when we go from one valley to the other.
Could you please say what real physical system you had in mind in this calculation?
These are all toy systems that are used to make a point, and to tell you what happens and why in certain cases the constraint minimization may be right, and in some other cases the constraint minimization may not be working. And so why in the first case it works is because the reaction coordinate that you estimate from here somehow is not that different from what really happens at the certain point. So suppose that what we want to do is to break a bond, probably the atom-atom distance is a good estimate, okay? Because eventually what will happen is that this bond elongates and breaks, and so if you keep, if you monitor how the energy varies as a function of the bond length, then you will pass through the southern point. Even if some other variables in the system will adapt, so I mean, you are not going through the linear interpolation because the other degrees of freedom will adapt. But basically, what happens at the breaking point is basically what you suppose that this bond breaks. But there may be other systems, like suppose that, I don't know what they think is rotation. So at a certain point, a molecule may need to rotate and break. And then the rotation may be, I mean, something that is not easily defined as in the linear interpolation. So what happens is, the reason why this doesn't work is because the path, I mean, the reaction coordinate that you get and the reaction coordinate that really, the tangent of the real reaction, the minimum energy path, have a significant angle. And so that when you minimize in the direction orthogonal to this, to the one that connects directly to the images, you are mixing steep variations with rather shallow variations. Instead, in the NEB, what you do is that you have minimized with respect to the shallow all the shallow variation, and you are so basically you have steep negative objects, negative eigenvalues, and shallow positive eigenvalues, and then when you mix them, if you constrain your minimization to mix them in a specified ratio, then the minimum may be the minimum may be located in a place different from what you have. So what you think. So somehow if the angle between the true and the guessed reaction is large, so if your chemical intuition is not good enough, NEB should in principle adapt and find the right thing, while the constraint minimization will in general not do that. So this is the point.
This generic feature is for single bond breaking at a time, or it can have multiple?
Well, this is what you have when you are looking for one single, and usually this is what you do. You always look for one single process, and you are not looking to multi step activated processes, because each one is rare, and so usually you are looking for reactions in which you only have one barrier at a time.
But in this case you have to do that.
In the other case you have to write. This is true. Yes?
Are you guaranteed to always get the point at the side point?
Well, the minimum energy path pass through the standard point. Let me go to the next thing. How do you tell this thing to the code? You have to specify that you want to do a net calculation, And then, okay, then you have to specify if you want, but this is optional, how many steps this iterative minimization should go on. And then you need to specify how many images, so how many replicas you take in order to go from the initial to the final scheme, to the final configuration. And then there are some other things that you can specify, the optimization scheme that could be quick mean, some steepest descent or Broyden. And then there is this climbing image scheme. So in principle you have a chain, and this chain will locate at certain points along the path. Not necessarily there will be one at the saddle point. So by specifying this climbing image at a given point of your minimization, you can say that the highest, for instance, if you take this climbing image automatic. So if you say automatic climbing image, what the code will do is that at a given point, the highest energy, the highest configuration, the one which is likely closer to the saddle point, will actually be moved up along the tangent. So usually you minimize everything, including the energy associated to the spring. When this climbing image scheme is activated, there will be one that is actually pulled up along the path, and so it will end up being at a maximum along the path. So it will be a minimum with respect to all the other coordinates, and it will be a maximum along the path, so it will be at this other point. And you can either do not choose this option, so this is what you do at the beginning, because you do not know where this saddle point will be. So you let things go for a while, and then when you think everything is more or less settled, you switch on, and you can switch on it either automatically, saying choose the highest one, or manually saying I want that the fifth image goes to the saddle point. This is one thing. This first last optimization is that in principle you may also start from configuration that are not in which the reactant and the product are not yet fully optimized. So the first and last image may not be exactly at the minima, and so you can want to do this along the neb. But usually this is something that I don't think is really useful, because it's so much easier to relax the initial and final configuration than doing the neb, but that there is no real point in willing to do it together. And then the other thing is this K max and K min. I said that this K, this spring constant, define what is the penalty along the path, and so somehow is related on to how close the subsequent images are. No? So if you have it along the chain, you have some loose spring and some very stiff spring. What will happen is that around the stiff spring, the images will be closer, and around the looser springs, the images will be farther away from each other. And so by giving different value of K max and K min, you can kind of try to get more resolution where the energy, where the close to the saddle point, and forget about forget about the details where the energy is smaller, where the energy is far from the saddle point. How do you specify intermediate image? If you want, always you need to specify in the atomic position. So if you specify neb as a kind of calculation, then you need to specify a first image and possibly there are, as was mentioned today, you can say that certain component of the position shouldn't change in the first image. But let's say you specify the first image, and you always need to specify the last image. Suppose this is a system with 3 atoms, X, Y, Z. If you have, for some reason, you think that the path should go through some intermediate configuration, then you can specify intermediate image. This is optional, but you can specify as many intermediate images as you want. I think no more than the actual number of images. But, you can specify a number of them. Okay, so this is simple case, simple example. This is hydrogen molecule with that interact with an hydrogen, which is attacked by an hydrogen atom, and we are studying the transfer of the central hydrogen to the right. So the breaking of this bond and the formation of a bond between these two. Okay? So this is the reaction. Obviously, initial and final configuration have the same energy, and obviously we expect this thing to be symmetric. So if you do plain that calculation with 8 images, this is what you get at the end, and then the curve is just an interpolation, spline interpolation of the data.
See, in reality, if the hydrogen molecule form
Yes.
H2, does it accept so easily another hydrogen? So the activation energy should be very high. Both is it a physical chemical reaction in nature?
Well, there are, I don't know for hydrogen. Well, anyway, hydrogen, this is very reactive, I think. So it's, I don't know, the calculation says that this is 0.1 volt, which is not very high. This is,
But to bring the hydrogen from hydrogen molecule, I have to have very high energy, that is one the molecule form. Usually hydrogen does not want to break by itself to break the energy to accept.
yeah, but the point is that also the other hydrogen wants to form a bond. So I mean, there is a competition.
Depends who
It
is
does not, so
I don't know. Parents with these calculations. If you add, if one thing that you can do is that you can give some different value for the K max and K min, so that the images that are higher in energy are also have stiffer springs, and so what happens is that with respect to the previous case, what you see is that the images close to the, at higher energy, so therefore close to the activation energy, are closer. So you have better resolution along the path there. You lose some resolution in the side, on the side, but you are not interested so much there. You are interested in the region around the activation energy. And the other thing that you can do is, although the system is symmetric, and although you are doing calculation with eight images, you can specify that you want to put one, in particular the fifth image, on the top. And so at the end of the relaxation, at the end of the minimization, this is what you have, is that system break, if you want symmetry, but the result that you have is that you have one image at the top. So in the afternoon we will see some practical example and how to set the variable for the net in reality. This particular case is actually example number 17 in the distribution. So if you look this afternoon in the quantum expression distribution, there is a subdirectory called examples, and inside there are a number of examples, and example 17 that basically this okay, that's it.
The thing on your screen? I've seen that before. Your screen on your iPhone?
5 minutes.
Yeah. There's another good one I found. I don't know if you've ever seen this. It was the question was expand